Alright everyone, so next we are going to discuss electronic circuits and the simulations that we are going to carry out using different electronic components and how they are used in some of the electronic circuits. So some of the electronic circuits that we are going to look into in this course are rectifier circuits that converts AC voltage into DC voltage, and the component that you see on the screen, diode, is going to be used to rectify the AC voltage into DC voltage. And then we are also going to see circuits with bipolar junction transistors, BJT, and you are going to see some amplifier circuits, voltage amplifiers that will amplify the input voltage and produce a higher voltage at the output pin. And then we are going to see one circuit at least with the MOSFET, which is the metal oxide semiconductor field effect transistors. So we are going to study these three very basic electronic components, and we are going to carry out simulations with these three components, starting with the diode, what we also called rectifier diode or PN junction rectifier diode, as you can see on the screen. So the basic quality of diode is it is an electronic switch. So anode is the positive side and cathode is the negative side. And if the voltage of anode is greater than the voltage of cathode, based on what type of transistor, what type of diode you are using. For example, if you're using silicon diode, then if the voltage of anode is greater than the cathode by 0.7 volt, then diode turns on and it lets the current pass through it. And the voltage drop across the diode is 0.7 volt, because that's the voltage that it has to overcome, the power supply has to overcome to turn the diode on. When the voltage is on anode is greater than cathode, this is called the forward bias. So forward bias operation, or diode is supposed to be in the forward biased region, and diode is considered to be on. Actually, theoretically, when the diode is considered to be on, we assume that it is a short circuit, so we don't consider any voltage drop across it, but practically and through simulation, you will see that there is a voltage drop across it when diode is going to turn on and the current will be passing through the diode. And if the voltage on cathode is greater than the voltage on anode, then the diode is supposed to be in the reverse biased position and diode switch is off. So nothing passes through diode and all the voltage appears across the diode. So from the positive side to the negative side, if you put the voltage probe, you will see that there is a negative voltage across the diode, which shows you that diode is in the reverse biased position and it is acting as a switch that is turned off. So I have put some detail of diodes, how does it work in the tutorial, and make sure you go over that. Again, the theory is not required in this course. You will study diode in semiconductor devices, in power electronics if you will take that course, if you're electrical concentration. But again, theory is not required, but it will be extremely beneficial for you to at least go through some of the basic stuff about the diode that I have put together in this tutorial. So when you actually see the diode, and some of you actually would have already played with the diode, but once you take semiconductor devices, perhaps that will be the first course where you will be using diode. So at that time, diode will not be a new component for you if you read some of the stuff that I have put together, which is very basic stuff about the diode. Basic diode circuit, again, I will highly encourage you to do all these circuits, create these circuits in PSpice and run the simulation as I am running and see if you are getting the same results. Basically right here, I am running the DC sweep simulation. So remember, all four types of simulation that we have studied, all those simulation will be valid for all the electronic circuits that we will be discussing. So we are not doing any new simulation. Those four types of simulation, bias point, transient analysis, DC sweep and AC sweep, those are the 4 simulations that you have already done in the first 2 weeks, and those will be repeated for rest of the semester. So the first one I'm showing you is the DC sweep, as how if you are changing voltage across a diode, how the voltage is dropped across a diode. So input, this is the diode voltage on the x-axis, and then looks like, let me see what I'm doing. Sweep the input voltage. So I'm sweeping the input voltage and I'm observing the voltage across the diode. So input voltage is going from negative 10 volt to 10 volt, and then this is the input voltage VV1, and this is the blue line represent the voltage across the diode when you put the probe from the node 1, which is here, to the node 2, which is here. So from positive side to negative side of the diode. So as you can see, when voltage is negative, diode is off, so all the voltage will appear across the diode. Since there is no current flowing in the circuit, so there is no voltage drop across the resistor, and all of this voltage will appear across the diode here. As you can see, negative 10 is starting until the diode is going to turn on around 0.7 volt, as I told you, since we are using silicon diode. And then once it will turn on, it will hold on to that 0.7 volt and it will let the current pass through it. So that's what it is shown in this simulation. Once again, go ahead and do the simulation. And diode voltage and current characteristic, we discussed the diode voltage characteristic, and this is the current characteristic, as there is no current passing through the diode as long as it is off, and when it is turned on, that is the voltage across the diode becomes constant, then the current start increasing as you are increasing the input voltage. Okay, now this is called the half wave rectifier, and this is your sinusoidal source. So basically what's going to happen, that when your input voltage is positive, because this is a sinusoidal source, remember, so it's going to create a sinusoid. So when in the positive cycle of the sinusoid, diode is going to be on after the input voltage reaches to 0.7 volt, and once the diode turns on, 0.7 volt will be dropped here and rest of the voltage will appear across here. And in the negative cycle, or when the voltage drops down below 0.7 volt and the whole negative cycle of the input voltage, diode will be off because the cathode voltage will be higher than the anode voltage. And once the diode turns off, then of course the switch is off, no current will pass through the diode, and the output voltage will be 0 at that time. So this is called half wave rectifier. Why? Because only the positive input cycle is passed through the diode and appears across the output load, and the negative cycle is stopped by the diode, so output becomes 0. So the AC input voltage, AC voltage has both positive and negative cycles. The AC input voltage is converted into a bipolar input voltage converted into unipolar at the output. Now it's not a constant DC, it's not a constant value, but it has the diode has basically eliminated the negative cycle of the input voltage, and the output is only the positive cycle or 0. So this is called half wave rectifier circuit, and this is called pulsating DC. So this is the output voltage. So you have the positive cycle and 0. So the negative cycle is gone. This is the voltage across diode on top. So when the diode turns on, 0.7 volt, and when it turns off, all the negative voltage appears across the diode, right? And this is the output voltage right here. When the diode turns on at 0.7 volt, then the input waveform appears across the output, because diode will just drop 0.7 volt constant. So the output waveform is not 5 volt, it's 5 minus 0.7, 4.3 volt peak. And then as soon as it will go down below 0.7 volt and then goes in the negative cycle, the diode will turn off and the output will become 0, because there is no current passing through the resistor, so the output will be 0. So the negative cycle is gone from the output. This is called pulsating DC. It's not called constant DC, it is called pulsating DC. And then this pulsating DC can be made constant by putting a capacitor in parallel with the resistor to create a filter. And actually we are going to study the effect of filter capacitor in the exercise that you are going to perform for the next homework. So again, go over this, and what I'm going to show you, I'm going to create this circuit and then show you the output of the circuit. So this is called the full wave bridge rectifier. The one that I showed you, this is called half wave rectifier circuit because it is only rectifying half of the waveform, only the positive side and negative side is gone. This is called full wave bridge rectifier circuit. There are two different types of full wave circuit, full wave center tapped rectifier, and this is called full wave bridge rectifier because these diodes, 4 diodes, are creating a bridge basically. And the characteristic of a full wave rectifier circuit is that both the positive input voltage and the negative input voltage appears to be positive in the output. And hence it's a full wave bridge. So both waveforms, the positive waveform and the negative waveform, becomes the positive at the output, and you have the complete rectification. So this is a full wave bridge rectifier. These diodes are present in eval library. So the eval library you used, already used to get the switch in one of the exercises, in the same library you can find this diode. And there is also a diode library in the PSpice that you can also add, and this component is also present in the diode library. So I'm going to go ahead, and I already created this circuit right here. And I'm just using eval library. I'm not using diode library, but once again, if you want to use, you can use the diode library as well, which is right here. And diode library has bunch of different diodes, a lot of different diodes, and this diode is also present in the same library. I'm just getting it from the eval, which is somewhere right here, D1N3 4002, right there, this component. Input is a sinusoidal waveform with 5 volt and 1 kilohertz frequency, and for the load I'm using a 1 kilo ohm resistor. So we are going to run this circuit, transient analysis, because input is AC waveform. So we're going to create a transient analysis. I'm going to go ahead and create a simulation. And now run to time. So how much time do you want to run the circuit for? So let me just tell you, if it is not given to you, but if you're using the AC waveform, the sinusoidal waveform, a good estimate of how long you want to run the circuit is about 3 to 4 cycles. 3 to 4 cycles. So if you look at the frequency of this circuit, it's 1 kilohertz. That means the time period of this is 1 over frequency, which will be 1 over 1 kilo, 1 millisecond. So the time period is going to be 1 millisecond. So in 1 millisecond, it will have 1 complete cycle. So if you want to run it for 3 to 4 cycles, that's going to be about 3 millisecond or 4 millisecond. So let's say if I run it for 4 millisecond, 4 cycles. And I just want to save the data right from the get-go, so 0. And then a good estimate of maximum step size is whatever your one time period is, which is 1 millisecond over here, take 1/100th of the time period. So plot 100 points in each time period, in each cycle. So 1/100th of the time period is a good estimate of maximum step size. You will have enough points so that your curve is going to be very smooth. So 1 millisecond is your time period. So I'm going to take 1/100th of 1 millisecond, 0.01 millisecond. I'm going to apply this, and okay. All right, so I'm going to go ahead and run this simulation. All right, here you go. So what I'm going to do, let me go ahead and put the probe. So what I'm going to do, I'm going to put one probe at the input, and then I'm going to, so how the circuit works basically, in the positive cycle, D1 and D2 turns on, they turn on, and the current flow in this direction along my mouse. So it goes here, passes through D1 because it is on, then it passes through R1, then it passes through D2, and then it goes back to the other side of the Vs, which is grounded. So it goes back to the ground. And in the negative cycle, basically, when the bottom part of the source is positive with respect to the top part, current comes out from here, goes through D3, which becomes forward bias in the negative cycle, then goes to R1, then D4, and then go back to the other side of Vs. So in both cycle, observe that the current is flowing in the same direction through R1, from left to right. And hence, the voltage across R1 will be in one direction, right? So it's not going to change its direction, hence the rectification is going to happen. So I'm going to put, I cannot use a single-ended probe to measure voltage across R1 because none of the node of R1 is grounded. So I have to use the potential difference probe. So I'm going to put one probe here, which is the positive because current is going in the left hand side and coming out of the right hand side of R1. Okay. So now I go to the simulation, observe, this is your output, right? So the green one is your input voltage. So you have sinusoidal input voltage with the peak value of 5 volt, right? And then the red one is the voltage across your diode, or the load, sorry, not diode, load. And of course, you see that it's starting a little late because the voltage across the two diodes. So each diode has to drop 0.7 volt when it is turned on. So basically, the total voltage drop across both diodes which are turned on will be 1.4 volt. So rest of the voltage will appear across the output. So that's why you see here that the peak value is much lower than this. And it is lower about 1.4 volt. This is about 3.6 volt, which is 5 minus 1.4, right? Because 0.7 volt each is dropped across each of the diodes. So total voltage drop in one direction is 1.4 volt. So here D1 and D2 are on in the positive cycle, and when the input has the negative cycle, then D3 and D4 will turn on. So in the first cycle, D1, D2 are on. In the second cycle, D3, D4 are on. But since the current is flowing in the same direction through the load, since I'm measuring the voltage across the load, then I will have the same voltage direction. It's not changing its direction because the current is going through the load in the same direction. So this is the output of your waveform. And again, if you want to measure it, since I closed the window let me go ahead and open that, my cursor window right here. If you close any window, you can go to view and then you can open those windows. I'm going to open my cursor window. And then if I want to measure, let's say, go to the peak right here. So observe, I'm at about yellow cursor. I can also use this for the peak, so it goes to the second peak, and which is much accurate if you press the peak cursor peak anyways. So my green, which is the input, is about 5 volt, 4.997, and my red, which is my output, is about 3.719 volt. So about 1.4 or a little less than 1.4, about 1.3 volt. So when it turns on, it's about 0.65 to 0.7 volt. So this is my peak output. This is my input value, the peak input value. Right? So this is how the circuit is behaving. This is called pulsating DC. So it's not a constant DC output. It's a pulsating DC output. It has pulses. Now you can make it constant DC output. And that's what your exercise is. So this will be your exercise for the next week, one of the exercises for the next week. And you are basically creating this circuit that I just created and I showed you the output. But what you're going to do, you're going to put a filter to smooth out the output. Instead of pulsating DC, you are trying to make it constant DC. And how are you going to do that? You are going to take these capacitors one by one. First, go ahead and put 1 microfarad in parallel to RL. So over here. So you're going to put 1 microfarad in parallel to RL. And then you are going to observe the output. You will see that your these pulse, it's going to become a little smoother. So it's going to go like this. And then you're going to go ahead and take that 1 microfarad out of the circuit and replace it by 10 microfarad. And then observe the output again, run the simulation. Every time you change the capacitor, you have to run the simulation. Run the simulation, observe the output again. And you will see that it is going to become, the output is going to become more smooth. It's going to become smoother. And finally, you're going to replace 10 microfarad by 100 microfarad, run the simulation again, and you will see it will become very smooth. It will become almost DC voltage, constant DC voltage. So this is how you are going to do this exercise. And yeah, with this, the discussion of diode for this course is done.